Hi, everyone. My name is Elaine Famutimi, and today I will be presenting forecasting solar radiation over Puerto Rico. Introduction. So high variation in cloud cover and cloud shadows can present a challenge for generation of energy using solar power systems. Shadows generated by these clouds impact power generation capabilities. For example, power generation using photovoltaic and concentrated solar power systems experience drops in power called ramps, which are high amplitude fluctuations of the available solar energy. Accurate ramp predictions of minutes to several days are required by grid operators to balance supply and demand of the electrical grid. Accurate forecasts also allow them to optimize scheduling of power production, which in turn benefits the environment by reducing carbon emissions. So there are several motivations to this study. Numerical weather prediction models struggle with predicting solar radiation to certain types of clouds. So satellites can field the gap to short-term forecasting below 30 minutes and long-term forecasting above 3 hours. Machine learning methods can also improve solar forecasting. We are focusing on Puerto Rico since it serves as a good model to their year-round sunlight, and also this study will benefit them since they need decentralized power because they get a lot of power outages because of the tropical storms. So objectives. So in order to understand the machine learning predictions, we first have to understand cloudiness patterns over the island of Puerto Rico. So we developed a set of maps that points to areas of high cloudiness over the island of Puerto Rico. Another objective is to investigate machine learning methods that could be optimal in forecasting solar radiation, and hopefully the future machine learning method can forecast 3 to 5 hours ahead, and we can compare that to the output of the existing Stereocast model. So before I talk about the machine learning method, I'm going to talk about the Stereocast model, which was written by the Cooperative Institute of Atmospheric Research in the Sciences in Colorado State University. So it works by retrieving cloud informations from ClaverX files, specifically, like for example, cloud top height or cloud optical depth, and it matches wind information from local forecast systems to affect or move the clouds forward in space and time. But unfortunately, there are some limitations. For example, there's no cloud evolution, which means that the clouds aren't changing with time. Clouds also do not properly move with the wind, and it is computationally expensive. So now that we discussed what the Stereocast model is, we can discuss our new method. So like I said earlier, in order to understand how in order to understand the predictions of machine learning, we have to understand the patterns of cloudiness. So we did that by downloading GO16 satellite data, specifically the Clear Sky Maps data product. I then used Python to evaluate patterns in cloudiness for the season by creating a map and a time series. I also determined inputs that are needed for the current Stereocast model, which will also be used for the future machine learning model, which includes ClaverX files that I mentioned earlier, specifically the cloud map and the cloud cover data. And the determined output will be the global horizontal irradiance, which stands for the total solar radiation over a horizontal surface. And then at the end, create a basic machine learning workflow, which can be used for the future machine learning model. So this is the time series, which was done on Python. And what I found was that the autumn season has the most amount of cloudiness, while the winter season has the least amount of cloudiness, and cloudiness is mostly concentrated around the times of 2 to 5 p.m. It's also mostly concentrated in the lower right of the island, and increases towards the middle during the spring and summer seasons. And this is where the Cordillera Central mountain ranges. There's also high cloudiness on the upper right of the island where the El Yunque National Forest. So basically cloudiness is mostly concentrated over mountainous regions. So what is machine learning? So I find that machine learning has become quite a buzzword, but not a lot of people actually seem to understand what it is. So I'm going to give a brief history. Artificial intelligence arose in the 1950s with the idea of automating tasks usually performed by hand. The old approach was called symbolic artificial intelligence, which used a handcrafted set of large rules, which was later replaced by machine learning, which focused more on actually learning how to perform the tasks instead of using rules. In order to properly do machine learning, it requires input data, an example of an expected output data to compare with the predicted data from the machine learning model, and a measure to test that the algorithm is actually doing a good job, which is the learning part. So deep learning is a subfield of machine learning, which uses layers of representations that remodel with neural networks. And neural networks consist of layers connected via nodes, which form a network of interconnected nodes. So this is the general model workflow. So before I use any machine learning algorithm, this is what I'm going to follow just to get ideas down. So first I downloaded Python, which I've already been using, and I installed the Keras deep learning library with a TensorFlow backend. I then have to define the training, target, and validation arrays for tensors. So first I have to normalize all of the input data between the values of 0 to 1. I then have to select the type of model, which can be neural network or long short-term memory network. So training data is basically what the model is fit into. The target data is what tests the data to make to give accurate predictions, and then the validation tensor is what allows you to monitor if the model is being accurate. So the reason why you're training the data is to get a vector containing the output data and also containing the weights, and basically weights are what represents like how strong the connection is between the data points. And then I also need to calculate a training error, which is what the optimizer uses to calculate a new weight. So it's basically creating like a feedback mechanism. And then you also have to validate the data. So K-folds validation is just one method out of many, and it basically involves using data that wasn't used during the training portion of the model to see if it can still make accurate predictions. And it does that by splitting the data into equal portions. So then the validation is basically accepted once the data is no longer being overfitted or once it has found the correct number of weights. So future work involves reworking the existing Stereocast model to take large amounts of data so that I can compare the output of that model to the output of the machine learning model. Like I explained earlier, pre-process the data and apply machine learning algorithms using more Python libraries such as scikit-learn. And I'm going to try various machine learning models like neural network or long short-term memory, which is a type of neural network, until the output is better than that of the Stereocast model. And that's all. Thank you.
We can take a couple of questions for Elaine. Yes.
Hi, so I had a question about machine learning and asking how your experience was. I'm not sure of your familiarity with it, but could you elaborate a bit on like how you felt your experience was learning it or just dealing with it in general?
So I'm currently in the learning process. The model is just like, the workflow that I did is just how I'm going to go about actually doing machine learning. So I'm still trying to gather all of the data that I need, like the Claver X files. I don't know if I mentioned it. So I'm still waiting on that to go on and actually do machine learning. But learning about it is, it can be hard. It's very dense.
Okay. John,
Yeah, that is very interesting and useful work. One question is that, do you plan using all the spectrum of measured ghosts or radiance, or just use specific? Because radiation, particular radiation only focuses on visible. Do you plan to using the infrared sensor channels?
I don't think we are going to use any infrared channels. I think we're just mostly using a lot of cloud information for the most part. If that answers your question.
so you're going to analyze satellite data measured by satellite or just the retrieve cloud products?
Yeah, we're retrieving the cloud products and we're predicting the radiance.
I think you're using the retrieve cloud products to predict the radiances. Okay.
Yeah,
Yes.
we can talk afterwards.
In addition to Stereocast, have you ever considered using something like the high resolution rapid refresh or other modeling systems that really try to predict clouds too? Or is that completely useless, you think?
I really haven't looked into that. I'm just mostly using Stereocast because that's what Sierra is using and they fund the research. So I'm just trying to improve on the models.
It could be interesting to find out
Yeah.
too that the cloud forecast is not useless.
Let me add in here quick thing. I'll comment on that. So Elaine joined last fall semester and she spent last one semester continuing learning Python. She's new to Python. She learned a lot Python. She's learning coding. So that's the great achievement, Elaine, and I'm really proud of you. Any questions? Yeah.
Very good.
Yeah, I have a question. Like, great work, by the way. I'm curious. You mentioned that you were quantifying the cloudiness based on those like satellite images. How are you exactly doing that? Like based on Python? Are you using like specific package or just like, yeah? What are the methods you're using for that?
Yeah, I'm using various packages like GeoPandas, Cryptography. For the most part, I have to write like for the time series, I had to write a loop to get all of the data from 2019 to 2020.
Okay, but you're loading in like a radiance data or
It's
like
called
the images itself?
for the time series, I am using like an actual image. I guess like a data file that can turn into an image. So it's called the cloud mask. So it basically is a binary 0 to 1. I think 1 shows that there's clouds, 0 shows no clouds.
Oh, sounds good.
But then,
You run that mask to the image basically and then quantify cloudiness from that.
Yes.
Okay.
Okay, let's